Ionic substances are very common on the Earth's crust. They occur as minerals. They're also present in the foods that we eat. They're just everywhere. They are generally very stable because those ionic bonds between the ions are strong. And they tend to be solids at room temperature and have very high boiling points. Examples of ionic compounds that you might ingest, Morton's light salt. What makes it light is it's a mixture of sodium chloride and potassium chloride. Sodium is the ion that tends to raise your blood pressure, and that, people need to be on a low sodium diet, but they still want some salt on their food. You can use Morton's salt because it'll give you some of that sodium that you want the taste of, but it's mixed with potassium chloride. And potassium is the other ion your body uses, and if you're getting them in balance, it affects your blood pressure less than if you're just taking in a bunch of sodium. Calcium carbonate is the active ingredient in antacids like Tums. That's an ionic compound, a calcium ion and a carbonate ion. Calcium carbonate is also found as a mineral known as calcite. Swallowing one of those crystals would not be as effective as an antacid. Yesterday they were asking me, but could you make it out of that? Yeah, you could. Basically, the Tums has a texture and binding agents such that when you chew it, it crunches up easily so you can swallow it. And then it dissolves in your stomach, and so it's available to neutralize the acid. In order for this to be effective, you would have to crush it into small bits so that it wouldn't just be one lump sitting in your stomach. Trona is a crystalline form of this messy formula. So most of the beautiful rocks that we see are actually crystalline forms of ionic compounds. They're all over the place. So we're going to learn how to write formulas for ionic compounds and also how to name them. So here are instructions for writing formulas. You need to look at the formula, the symbol for the metal cation, and you need to know its charge. And you need the symbol for the nonmetal ion and its charge. You have to write those down, and then we're going to adjust the subscripts. We're going to figure out how many cations, how many anions do we need so that when we put them together, we have a neutral compound and we have the lowest ratio. And then checking your work is always a great idea. Check at the end to make sure that those charges are going to add up to 0, because compounds are electrically neutral. They don't have a charge. Ionic compounds always have positive and negative ions. The first element is almost always a metal. There's one exception we need to know about, and that is ammonium ion. This was on that list for you to memorize. This is the only polyatomic cation that we're going to deal with in this class. So if it has a metal, if it starts with a metal, boom, that's an ionic compound. If it starts with NH4, it's also an ionic compound. So we got to have the sum of the positive charges be equal to the sum of the negative charges. And it's always going to be the smallest whole number ratio. So let's write formulas for ionic compounds that form between potassium and sulfur. So we need to start out with what kind of an ion, K is the symbol, what kind of an ion does potassium form? What charge will it have? It'll have a +1 charge because it's in group 1. Group 1 metals make +1 ions. Group 2 metals make +2 ions. Group 3 metals form +3 ions. That's kind of convenient, right? And then sulfur, what's the charge on a sulfur ion? -2. We write S2-. And what we learned there is that these atoms are going to gain or lose electrons to have the same number of electrons as the nearest noble gas. So for the nonmetals, I think the easiest way is to look at the periodic table and start with the noble gases. They don't form ions. They're going to be 0, and then count backwards. -1 for group 7, -2 for group 6, -3 for group 5. And those will be the charges. And they're predictable. They're always the same. So that's the first step. Symbols of the ions with their charges. Then we have to figure out how to put them together. And this is where people's thought processes are different. Some of you can look at that and say, oh, well, we need 2 potassiums and 1 sulfur. What's so hard about that? Other people are going to be like, I don't know what to do here. Okay? So I want to show you how it works. The best thing is to really understand what's going on here. And then I'll show you a shortcut that you can get the right answer most of the time without understanding anything. I don't recommend that, though. So one approach is to just sort of keep a running total here. How many positive charges do we have? Well, we've got +1 from the 1 potassium ion, and we have -2 over here from the 1 sulfide ion. Do these numbers add up to 0? No, they don't. We need more positive charge here, don't we? So we can't adjust the charge on this. We can't take away any. All we can do is add more ions. So we'll add another potassium ion. Well, what if we have 2 of those? Well, now 2 of them, we've got a +2 charge overall. So the total charge on these 2 ions is +2, and from this 1 sulfur, we get -2. And so +2 and -2 add up to 0. So we write the formula as K2S. So there's 2 potassiums and 1 sulfur. Any questions? The shortcut is a method that we tend to call crisscross. So if you take those ions again, you still have to start out with the ions with their charges. What we're going to do is we're going to take the charges, the number from the charge, and bring it down and make it the subscript for the other ion. So this 2 becomes the subscript for the potassium. This unwritten 1 becomes the subscript for the sulfur. So we get K2S. We didn't write the 1 here, and we're not going to write the 1 down there either. This is going to work most of the time, provided that these charges are not the same. If the charges are the same, we don't need to do anything. You just shove them together and it's good. So if they're different. But this can get you into trouble sometimes because it will not always give you the lowest ratio. And so you do have to watch out for that. Any questions?
But you can always simplify it, right?
You could simplify it, yes. But you have to remember to do that.
So most of the time when you want the simplified,
It needs to be the simplified, the lowest ratio, because that's what ionic compound formulas are. And I know that the naming rules can be a bit overwhelming. It's a little bit like learning how to play bridge. I mean, I don't know how to play bridge. I know it's a card game that some people really, really like. I've learned a little bit about it, and I'm like, that just doesn't sound very fun, right? And so this might be like one of those complicated, non-fun card games, but you signed up for the class, you got to learn how to play the game, right? And here I am explaining the rules to you. And just like when you're learning a game, you can read all the rules, but they don't necessarily make sense until you begin to play the game. And the other people say, oh, no, you can't do that because there's this rule. And you're like, oh, yeah, that's right. After you've played it a while, then you understand the rules and you remember them. This is a thing that's going to require some practice. You're going to make mistakes, learn from the mistakes, and get better at it. Okay, let's look at the compound that would form between nitrogen and aluminum. So aluminum is Al. What charge does an aluminum ion have? +3, because it's in group 3A. Nitrogen has what charge as an ion? -3, as you count back from the noble gases. Here, we're not thinking of nitrogen as being a diatomic element because it's with aluminum. Question?
Does it matter which side the negative and positive is?
Actually, it does matter. So we write the sign after the number. And I think the reason we do that is because we don't want it to look like math. We did it the other way. That looks a lot like a variable, capital N, raised to the -3 power, right? So this looks like math, and that looks different. Okay, so we always put the number first and the sign after. We always write the sign, like here, we're writing the sign even though we didn't write the number 1? So that's a good question. And we always put the metal first and then the nonmetal. Anybody know why? It's one of my favorite reasons. Because that's how we decided to do it. It's convention. And here the masculine feminine thing comes in as well. If you're addressing a formal invitation, say to a wedding, are you going to say Mr. and Mrs. John Smith or Mrs. and Mr. John Smith? It's Mr. and Mrs. Is that because the world is out to oppress women?
Yes.
No. You can interpret it any way you want, but it isn't. It's just how it's always been done. And it just makes life easier when we do the same thing. There's no significance attached to it. So here, the cation always goes first and then the anion. You think of the metals as masculine, the nonmetals as non-masculine, as being feminine. It's Mr. and Mrs.
I always thought it was because of the order of the periodic table.
Well, it is the order of the periodic table. And the order is, even with molecular compounds, it's the more masculine, or the more metal-like, the more metallic of the nonmetals that goes first. But this Mr. and Mrs. works for me. Okay, so how do we put these two together so that they're neutral?
ALN?
Yeah, just ALN. Positive 3 and minus 3. The charges are the same, just opposite in sign. We don't really have to do anything. We just shove them together. So aluminum and nitrogen, ALN. So if you like the crisscross method, when you look at this and see they're both 3, you don't need to crisscross, just shove them together. If you did crisscross, you'd end up with Al3, N3, and then you should look at that and say, that's not the lowest ratio. I need to simplify that. Yeah?
When would you use N as a -1?
N would never be a -1 ion.
Never.
Never. Nitrogen only makes a 3- ion. It wants to have the same number of electrons as a noble gas. And so it's either going to be an atom or it's going to go all the way and be like the noble gases. There are reasons behind that, but we don't want to do that yet. When we name ionic compounds, all compounds have systematic names. A bunch of people got together and hammered out a system for naming things, and the goal is to be consistent no matter what language you speak, no matter what country you live in, that they all have the same formula, the same name, and that each has one that's agreed upon as the best name. Now, some of them have common names. Sodium chloride is the systematic name for NaCl. The common name is table salt, right? So there are things that have common names, but they also have systematic names. So we have to identify that it is an ionic compound before we can apply the rules for naming the ionic compound. Here are some examples. And you identify these by looking at the first element. Here it's a metal, that's an ionic compound. Aluminum's a metal, ionic compound. Calcium's a metal, ionic compound. Magnesium, metal, ionic compound. Okay? The only exception is when it starts with NH4. That's also an ionic compound. Books like to divide ionic compounds into 2 categories. I think it's dumb, but it's in there, so we're going to do it anyway. The first type of ionic compound has a metal whose charge is predictable. And those are the ones we've talked about so far, plus a couple others. So group 1, group 2, group 3 metals. They always have the same charge, so they're easier. The second type has a metal in it that can have different charges depending. It might be +2, it might be +3, +4, etc. So these are the metals that always have the same charge. And so we see there's group 1A, group 2A, group 3A, and don't worry that the rest of these aren't highlighted here. we rarely use gallium, indium, or thallium. So if we do, just say it's +3 and you'll be fine. And then there's this guy, zinc and silver. I'm going to ignore scandium. He only forms one ion, but he just doesn't show up much, so we can just ignore him and be fine. So aluminum, zinc, and silver. Aluminum's +3, zinc is +2, silver is +1. And I've got a slide coming up that helps us understand how to remember that. So these metals form just a single ion. They always have the same charge, and so the name of the ion is just the element name. Easy. Then the rest. Anybody who isn't one of those, and I remember them as groups 1A, 2A, 3A, zinc, and silver. I'll be saying that over and over and over again. Groups 1A, 2A, 3A, zinc, and silver. So elements that are not part of group 1A, 2A, 3A, zinc, or silver, such as these elements, can form more than one ion. So chromium can make a +2 and a +3 ion. And so we have to have a different name for each of these ions because they are not the same thing. And so we call this one chromium 2 with Roman numeral 2 in parentheses, and this is chromium 3 with Roman numeral 3 in parentheses. So let's have a quick review of Roman numerals. 1, 2, 3, 4, 5. Oh, I don't have room for 6. 6. Those are what are called Arabic numerals. That's what we use. The Romans used capital letters. So a 1 was 1 capital I, and 2 is 2 capital I's, and 3 is 3 capital I's. And you realize that if we kept going with this, 100 would be a bit tedious, right? So 5, I'm going to skip 4 for a minute. 5 is a capital V. I don't know why. The Romans just did that, okay? So it is. 5 is a capital V. 4 is 1 less than 5, right? So it's 1 before 5. 6 is 1 more than 5. So it's 5, and it's 1 after that. And guess what 7 is? V with 2 I's after it, because it's 2 numbers after 5. That's far enough. Things get really wonky when you get into the, well, 10 is X. I remember that one. And then there's L's and D's and M's, and I can never keep those straight, but we don't need them. L's 100. I think M's 1,000, but yeah, it gets confusing. So those are the Roman numerals. I think of these a little bit like naming kings or guys, you know, you have the same name as your father. So there was King Henry. There's King Henry II, King Henry III, King Henry IV, right? Same given name, we have to distinguish between them, so we use Roman numerals, right? So this is like chromium II and chromium III. We're using the Roman numeral to specify the charge. There's more than one of them, so we have to do that. My son, I'll pick on Andrew. Andrew Kawagoa. He is the only Andrew Kawagoa in the world, right? Does he need a Roman numeral after his name? Andrew Kawagoa I? No, he doesn't, because there's only one. Those metals in groups 1A, 2A, 3A, zinc, and silver only form one ion. So just like a guy who does not have the same name as his father, you don't need junior, senior, or Roman numerals after your name. These guys do. Any questions? So here's how to remember the ones that don't need Roman numerals. Okay, groups 1A, 2A, 3A, zinc, and silver do not use a Roman numeral. All other metal ions need Roman numerals. So group 1A, 2A, 3A, zinc, and silver. How do you remember the charge on the zinc and the silver? Well, there's this, it's kind of like a magic triangle here, or maybe it's a Bermuda Triangle, I don't know. But these guys in group 3A form +3 ions. So that's part of the group equals the charge. Then these guys, I think of this as going down the stairs. So aluminum's +3, zinc is +2, silver is +1. Zinc and silver are the ones you need to remember. Cadmium also forms a +2 ion only, but again, that's just not going to come up much. Okay? So group 1A, 2A, 3A, zinc and silver. We remember zinc because it's a step down from aluminum. 3, 2, 1. Okay? So those are the cations. Then we have to look at the anions, because the name is the name of the metal ion followed by the name of the nonmetal ion. So monoatomic ions, that means a single atom. So these are anions that just have one atom in them. So the nonmetals can make these ions, fluorine, chlorine, etc. The charge is predictable from the position on the periodic table. And just like women traditionally change their last name when they get married, these nonmetals change the ending of their name when they become part of a compound. So fluorine changes her name to fluoride when she becomes an ion. Chlorine, chloride. Bromine, bromide. Phosphorus, phosphide. So that "ide" ending tells us it's a single atom ion. So the charges, you can do group number -1 or count backward from the noble gases. So putting these things together, we name the metal cation first, and then we use the name of the anion. So just like the formula has the metal first and then the nonmetal, the name has the metal first and then the nonmetal. So KCl. This has 2 ions, potassium and the chlorine, but chlorine as an ion changes the ending of her name to chloride. So we get potassium chloride. Potassium does not need a Roman numeral because he's in group 1. CaO, we've got calcium and we've got oxygen. Calcium is in group 2, doesn't need a Roman numeral because it's always a +2 ion. Oxygen, when she becomes part of this compound, when she becomes an ion, changes the ending of her name to "ide", oxide. So CaO is calcium oxide. Any questions? Okay, let's name this Ag3N. So mentally or actually, divide this into 2 pieces. There's 2 ions. The first element is what? Silver. So I'm going to write silver. And then I need to ask myself, is it in groups 1A, 2A, 3A, zinc, or silver? Well, duh, it's silver. Yeah, it's in that group. Doesn't need a Roman numeral. So I'm just going to go on and look at the nitrogen. How do we name that as an ion?
Nitride?
Nitride. So we take the element name, nitrogen. Oops. Saying it, so I started writing it. And we change the ending to nitride. This symbolizes that nitrogen kind of got married, right? Here's the guy and the girl. And we're not going to go into why there's 3 silver ions and 1 nitrogen ion. That analogies can be taken too far. We're not going to talk about polygamy or anything like that. Okay, so how would we write the formula for rubidium sulfide? Yeah, so Rb has a positive charge because it's in group 1A. It's +1. And we find sulfur on the periodic table, and we count backwards from the noble gases, it's 2-. So you can do the crisscross method. You can go for the least common multiple of 1 and 2. You can draw pictures. We're going to end up with needing 2 rubidium ions and 1 sulfur ion. Any questions? So the second group is the ions that need the Roman numeral because they have more than 1 charge. Yeah. So we figure out what charge that metal cation has by looking at the charge on the nonmetal, and we have to kind of figure it out. So let's do an example here. CrBr3. So again, we're going to divide this into 2 ions. We got Cr and we got Br. So we're going to name the first one Cr is for chromium. And then we have to ask ourselves, is chromium in groups 1A, 2A, 3A zinc or silver? No, it isn't. That means it needs a Roman numeral, because all of the ones that are not in groups 1A, 2A, 3A zinc or silver, are you going to remember that? 1A, 2A, 3A zinc or silver needs a Roman numeral. So I don't know what it is yet. I'm just going to put the parentheses in there, leave a space, and I'm going to come back to that. And then bromine changes the ending of her name to bromide. Okay, that's not so bad. Now, how do we figure out what the chromium is? Periodic table is no help for this. Sometimes doing a reverse crisscross works, and sometimes it doesn't. So I'm not even going to go there. If you want to do that, that's on your own time. What we need to do is we need to look at the charge on the anion, which is -1, and we have to look at how many there are. I'm just going to do it out the very long way so we see what's going on here. There are 3 bromide ions because it says Br3. So I'm just going to draw 3 of them, each with their charge. I do not know what the charge on the chromium is, so I'm going to look at the total. I have a total of -3 from my anions. For this to be neutral, the total charge on all of the cations put together has to be +3, right? These have to add up to 0. There's only 1, and so it must be +3. If there was more than 1, they'd have to split the charge equally, and charges have to be whole numbers. So if this has got a 3+ charge, what Roman numeral do I put in parentheses? 3. 1, 2, 3. It is important that those are capital I's. Mastering chemistry cares a great deal about this. I had a student last semester. It looked right. She's like, why is it wrong? It's telling me it's wrong. And I looked at her work on the computer, and it looked right because a lowercase l and a capital I in that font look exactly the same. Yes, the charges cancel each other out, essentially. The +3 charge on the chromium combined with the 3 -1 charges give us an overall neutral compound. No, because the 3 tells us that there are 3 bromines. So if we wrote CrBr, and we know that bromine has a -1 charge, then the chromium would have to have a +1 charge. That's going to be a different compound. It actually doesn't exist, but we don't need to know that. So we're going to look at the charge on the anion and the relative numbers of them to figure out the charge on the cation. Some of you are going to have some struggles with this. Please come talk to me. I've got a lot of other different ways of explaining it, but I can't do all of that in lecture. So chromium 3 bromide. I just want to make very clear, this Roman numeral is not how many ions are in the formula. It is the charge on the chromium ion. There's only 1 chromium ion here, but it has a +3 charge. And so we write chromium 3 bromide. If we wrote chromium bromide and tried to do the formula from that, we would not know what charge that ion has. So we need the Roman numeral to tell us the charge. Any questions? Let's name this guy. Looks like Fez, F-E-S. So there's 2 ions, the metal and the nonmetal. What's the name of that metal? Iron. Is it in groups 1A, 2A, 3A, zinc, or silver? No. So it needs a Roman numeral. And then sulfur, it's getting a bit repetitive with the sulfur. That's sulfide. Right? Change the ending of the name to "ide." We have to figure out the charge on that iron ion. So we have 1 iron and we have 1 sulfide ion. We know the charge of the sulfide ion from its position in the periodic table. Now this one you probably don't need to draw pictures or anything, right? We have one of each. I know that from the formula. There's just one of each. So if this one's -2, that one has to be what? +2. So that's 2 plus. And so I put the Roman numeral 2 in parentheses. Because of the different iron ions that are possible, this is the one with the +2 charge. It's iron the second. Any questions? So here's a name. Write the formula. There's ruthenium-4. I don't think ruthenium was on the list of things I made you memorize. So then you know, if you don't know what it is, look it up. It's Ru. What does this Roman numeral tell us? It tells us the charge on the ruthenium ion. It's 4 plus. And then oxide, that's oxygen, and what charge does oxygen have as an ion? -2. So this is a situation where crisscross could get you into trouble. You look at these, they're not the same. We've got a 4 and a 2. If you do the crisscross thing, we're going to get Ru2O4. That's not the lowest ratio. So you'd have to simplify that to RuO2. Or you can have more of a thinking way, ruthenium 4 plus, oxygen 2 minus. Okay, I've got -2 here, I've got +4 there. I need to put another one of these so I can get -4, and now I'm good. What would this compound be? Are you okay? It's not a real compound. What about polyatomic ions? So polyatomic ions have special names. You know, why is my oldest son named James? Because we chose that name for him, right? And everybody uses it because that's just what it is. The polyatomic ions have names, and they just have their names. You got to memorize them. There are some little patterns within there, but overall it just comes down to memorization. So here's NaNO2. There's 2 ions. The metal is the first one. That's the sodium ion. Everything else is a polyatomic ion. It has a single name. Don't call it nitrogen dioxide or something. Nomenclature is not a place where we value creativity. We value conformity, following the rules. So that's nitrite. And so the name of this is the name of the metal plus the name of the anion, sodium nitrite. So let's look at these guys. So here's a table from your textbook. And you see that most of these have a single name. Many of those names end in -ate or -ite. There's a couple of oddballs like hydroxide and peroxide and cyanide. Those guys are a little weird. The rest of them end in -ite or -ate. We've got a couple here that have 2 names. There's hydrogen carbonate. The old name is bicarbonate. I will not use that on exams. It could show up in homework or something, though. I like hydrogen carbonate because it's a lot more descriptive of what it is. This is the carbonate ion with a hydrogen ion stuck on it. It's a hydrogen carbonate ion. So the charge goes down 1 for every hydrogen you add. Here we've got hydrogen sulfite and hydrogen sulfate. And then with phosphate, phosphate has a 3- charge. If you add 1 hydrogen, you get hydrogen phosphate. The charge goes from 3 to 2. But you can add 1 more and get H2PO4 with a -1 charge, and that's called dihydrogen phosphate because it has 2 hydrogens on it. Okay, so all of those guys have their own little special names. Most of those polyatomic ions are what we call oxyanions. They are anions that have oxygen with some other element in there. And within a series of oxyanions, there are patterns to the names. So if there's 2 atoms in the series, the one that has more oxygen atoms has the ending -ate, and the one with fewer has the ending -ite. So we've got nitrate and nitrite. The difference is the number of oxygens. The number of nitrogens is the same. The charge is the same. The only thing that changes is the number of oxygens. We've got sulfate, and sulfite. They differ by one oxygen. Some of them have more than 2 ions. They have 3 or 4 ions in this oxyanion series. So here we've got chlorate. This is chlorite. It's 1 less oxygen than chlorate. This is hypochlorite. So it's chlorite with even 1 less. Hypo is a prefix that means below. Where does a hypodermic needle go? Below your dermis, below your skin. Hypodermic, below the skin. Hypochlorite has 1 less oxygen than chlorite does. And then from chlorate, if we have more oxygen, we use the prefix per, which is part of hyper. Hyperactive child has more energy, right? So perchlorate has more oxygen. So you memorize the 8 version. The ite is the light version. For this particular one, chlorate has 1/3 less oxygens than regular chlorate. Bud Light has 1/3 fewer calories than regular Budweiser. It's the light version. Hypo is 1 less, and per is 1 more. And we see that these formulas for chlorine oxyanions are the same as for bromine oxyanions. We're just going to swap bromine in for chlorine. So hypobromite is BRO minus, just like hypochlorite is ClO minus. Chlorine and bromine and iodine are in the same family in the periodic table. They're nonmetals, so I think of them as feminine, so I call them sisters. So the sisters, it's like sharing clothing, right? Sisters get to be, grown-up size, and a lot of times they're the same size, and so they can just, well, here, I'm just going to switch jeans with you, or switch sweaters. So the formulas are the same. So guess what the formula for per iodate is? IO4 minus. The same as per bromate, the same ratio and charge. Per chlorate, all we do is change that element. Chlorine, bromine, iodine, and then that shows up in the middle of the name. So if you memorize chlorate and its pattern, you can actually write the formulas and names for 12 polyatomic ions. So memorize the 8s and the pattern. The only thing that's changing is the number of oxygen atoms. The charge doesn't change. So per has 1 more oxygen. 8 is the one you memorize. Ite is the light version, and hypo is below the light version. And just so you don't get confused, this is upside down of how the book shows it, because this is below, and so it needs to be on the bottom. Okay, so let's name these guys. I want to stress again, there's only 2 ions. Okay? 2 kinds. One kind of cation, 1 kind of anion. So if you need to, draw a line. There's the SN and there's everything else. So SN is the metal. What's its name? Tin. Is tin in groups 1A, 2A, 3A zinc or silver? It is not. It's a type 2. It needs a Roman numeral. We're going to put the charge off till later. Now we need to name this ClO3. Chlorate. You can actually, you can guess on some of those. It's got chlorine in it, so, it's got to be perchlorate, chlorate, chlorite, or hypochlorite. It's got to be one of those, so at least you have a 25% chance of guessing correctly there. Okay, so there's the outline of the name. Now we got to look at charges. So ClO3, we need to know the charge on that. It's -1. And then we've got this tin. We don't know what the charge is. We have 2 of these. So from the anions, we have a total of -2 charge. There is only 1 cation. We need a total of +2 charge, and so all of that must be on the 1 tin ion. +2 charge, Roman numeral 2. Questions? Write the formula for cobalt 2 phosphate. Well, what's the element symbol for cobalt? CO. And it's capital C, lowercase o. What does that Roman numeral 2 tell us? It tells us the charge. So the charge is 2+. And then phosphate. Okay, we need to know the formula for phosphate ion. It's PO4, 3-. So you all did a pretty good job of memorizing these things to pass the quiz. As you do these problems, don't just go look up the formulas. Try to remember them or figure them out without looking at anything except possibly the periodic table, and then check yourself against the list before you go on. But keep practicing these because these are not going away. So we have to figure out how to put those 2 together. Here we've got +2 and -3. We could do the crisscross thing, right? So CO, subscript 3 from this charge, and then PO4 is going to have a subscript 2.
But you have to put the PO4 in parentheses.
We have to put the PO4 in parentheses, because if we do it this way, that kind of looks like 1 phosphorus and 42 oxygens, and that's not what we meant. When you have more than 1 polyatomic ion, you have to put parentheses around it. You put the number on the outside. If you only have 1, there's not going to be any confusion, and so we're not going to write the parentheses if we don't need them. Any questions?